Okay. So believe it or not, these lectures have numbers. This is lecture 10. The last one we just fixed up was lecture 9. We just finished it up. I just posted the video, and hopefully you'll see it. So let's talk about what we're doing now. This is chapter 12. We're going to talk about sources of magnetic fields. What we've done so far is this force F comes from a charge moving at a velocity through a B field. Okay, and the same thing goes, the charges are moving through a wire in a B field. It's the same thing, right? These two are essentially the same. So that's fine, but what are we doing? We're basically saying, okay, we have some B field, and that B field has a charge moving through it. Okay, so there's a charge, and that charge is going to have some velocity moving through that field. That's it. That's all there is. I mean, it could be a wire too, right? We could just have some wire passing through, and of course we'll have charges going through the wire with some current. So either way, it doesn't matter, they're the same. All right, so let me just put here, same. Okay, just depends on what you're given, current or velocity in a charge. So, fine. But this B field that we're working with is some B field that's given. B has been given, supplied. It's external. And you don't know. How was it supplied? We don't know. If it's a uniform B field, you can guess, right? You can guess that it was done with a solenoid. We talked about that. We did all kinds of stuff. We did torque, right? And we did the Hall effect and mass spectroscopy, right? So we saw what happens if a particle moves through a field in an external given field. So we want to know, how do we produce a B field? Okay, so that's our goal for this little chapter. So let me move this up here a little bit. The thing is, here's what we're going to be getting into, and that is how do we calculate? I need to move this. Okay, how do we calculate B fields? In different circumstances, right? In differing cases. And of course, this is due to the moving charges, right? Because how else are you going to produce a B field? You have to have moving charges. So that's the question. Well, here's the thing. There are two ways. Okay, and so it's all depending on what you're given and what can we do. Okay, so we've We've talked about what we've done so far. We've seen that all of our things are happening through an already provided magnetic field. But okay, so let's go back a little bit. We're going to have to go back a little bit before we get to the two ways. There was these two guys, all right? Two guys walk into an experimental physics lab. In 1820, we have these two people. I'm just giving their last names, Biot and Savart. You can guess their nationalities. And they did experiments, okay? All kinds of stuff. And they wanted to know about the magnetic fields. So they had current, all right? So they had some current moving through a wire. And they were measuring the B fields. Okay, so they found an equation that worked pretty well for them, and in 1820, it's pretty fabulous that they were able to find this. These two guys, and they found that mu naught over 4 pi times the current going through the wire cross R over R squared. Okay, so let's talk about these things, all right? This is the equation Biot-Savart came up with, all right? We call it Biot-Savart. It's Biot and Savart, but whatever. Okay, so we don't have time to pay our due respects. All right, so what is mu naught? This is not the magnetic, the original magnetic dipole moment, the magnetic moment. That's not what this is. Mu naught in this case, unfortunately, is the permeability of free space. Okay, so the permeability of free space. You could call it a vacuum, you could call it whatever you want. Now, this is opposed to epsilon naught, which was the permissivity of free space. Okay, so this is the permeability versus the permissivity. I think I'm saying that right. Permissivity. Okay, and mu naught is equal to the permeability. Okay, so yeah, go figure. I don't know, but here's the point. Mu naught has a number assigned to it, and that is 4 pi, and we'll figure out, I'll tell you why it's 4 pi in a little bit, but 4 pi 10 to the minus 7 Teslas meters per amp. Okay, so here's your amp, here's your meters, and here's your Teslas. Okay, so that's actually, here's your meters. This is meters squared, so you're left with one of the meters left. Yeah, that actually makes sense. Okay, if you rearrange them and solve for mu naught, you'll notice that's the units. Okay, so let's keep going. If we integrate, obviously, we're going to get our B field. So we're going to get B field is equal to mu naught over 4 pi. And then we're going to do some integral along a wire. And Biot-Savart were using wires. They weren't shooting electrons into a B field. They were doing it with a wire. Okay, so let's look at what does this look like in a picture. I'm going to draw a wire here. And at any point along this turn, I'm going to say this is my DL, and right in there, and my radius for the turn, or I shouldn't say radius for the, my distance to this point here is R. And of course I've got some current going through this thing, through this wire. And at this point, I want to measure what is my, so it's this point that I'm talking about. I want to measure my magnetic field. And so what am I going to have there? I'm going to have dB, okay, at that point. What's happening? Well, this is the angle theta, and it's not even just that, it's actually that, right? So that's our angle theta. And if theta is equal to 0, then dB goes to 0, right? So right in here, I might want to know what the field is here. Okay, so this is my point 2. And I've got current going here, charge moving there, but the angle theta is equal to 0. So if theta is equal to 0, then dB equals 0. Obvious. Cool. So this thing right here is one way to get, at this point, the B field. What am I going to do? I'm going to do a integral from this dl all the way to this dl, right? I'm going to go and integrate the whole thing. So I'm going to start at A, and I'm going to go all the way to B, okay? So that my integral is equal to mu naught over 4 pi A to B. And there's all along the way are changes, right? So all along the way, I'm going to have I dl cross r hat over r squared. Okay, so this is definitely doable. And if you're a clever person, you can figure out how to do these things. And we'll probably do one or two just to do it, but we're going to have to make sure that it's easy, right? We can't, it could be quite complicated. So anyway, that is one way. To get our B field. Okay, one way solved. Now, there's another way, okay? And that is a nice, clever math trick. It's clever because it's very much, it's essentially another application of a Gauss's law situation is basically what we're going to do. So the second way. And that is to use Ampere's law. So we've got two. We've got Biot of R. And we've got Ampere. Ampere is just another Gaussian surface, clever math trick, okay? And not quite a Gaussian surface. It's all right, forget I said Gaussian. But it's, I don't know. Okay, it's Ampere's law. Let's do it. Ampere's law. Fine. So we do this integral, and it's an integral around a loop. Okay, so it's a complete integral. And it turns out that that integral is equal to mu naught times the current going through our loop. Everyone says, yay, because they would rather do this than Ampere's law. So let's do an example. We have a straight, very long straight wire, okay? And we're looking down the barrel of the wire. It has current I in it. So I'm going to say that so here's the wire. And let's say that the current I is going into the page, okay? And we're just looking down the length of the wire. Okay, so we're going to enclose this thing with a circle of radius r. Okay, and at this point right here, we've got a couple of things, and I'm going to move my r because it's not in a good spot. You are in a bad spot. Okay, let's put r here. Here we have the component of the B field in the theta direction. Here we have the component of the B field in the r hat direction. And our length, okay, of this little region in here, this little region right here, has a length dl. All right? So what does that mean? Of course, we're going to add up all of the dl's. There's going to be dl's all around this circle, and we're going to just add them all up, okay, and get our total B field. Okay. Now, in the Okay. So dot products. Let's do a dot product. So we're going to do DL dot B. All right? And that really means DL dot, and now I have B theta in the theta hat, and plus BR in the R hat, okay? But what is DL in? DL is in the theta hat. So it's really, let's change it to DL theta hat, DL dot B. And so we've got DL theta hat, but that's B theta hat plus BR R hat. What happens when we dot this with this? What are you going to get? It's a dot product. So it's the cosine of 90 degrees. Cosine of 90 degrees is 0, so you're going to get nothing. So the only thing that's going to pop out here is DL B theta. All right, so when we go to do this, when we go to do our integral, because we're going to say mu naught I equals the closed loop integral of B, we're going to end up with B naught theta hat dot DL theta hat. And of course, that's going to leave us with B theta hat DL, because this dot this is going to give us 1, right? So cool. Now we know what R is. What is the circumference? Because we're just going to basically do an integral, closed loop integral. So we're going to go from 0 to 2 pi, and 2 pi r, I should say. And that means our circumference is 2 pi r, right? So awesome. That's going to give us our B theta, 2 pi r equals mu naught I. Okay, so it makes sense that people would say, okay, at this point, why, well, before we say why, let's state what we're going to state before we even say why. So B theta hat equals mu naught I over 2 pi r. So theta hat, or in the theta direction, or B theta. Why is B theta, little theta there, why is that really the whole B, right? Well, I don't know if you guys remember, but if you put your thumb along the current, which way does the B flow? So we put our thumb into the page here, and our fingers are going to point in this direction. This is our B field, right? Our B field points in that direction. Our B field is entirely made up of B theta, okay? So that is why there really is no BR, okay? That is 0. BR equals 0 in this situation. So all we're doing is adding B together. So that is why B theta is equal to B, and then we're done. So you can finally just say B is equal to mu naught I over 2 pi r. Okay? So, good. Now, symmetry helps us. So there's all kinds of symmetries out there. We love symmetry. And symmetry is going to be our friend, always tends to be. And so we can apply Ampere's law as long as we have correct symmetries. So Ampere's law is great if you have symmetries. So to apply Ampere's law, we need symmetry. Okay? So what can we say here? Let's sum this up. We've got our two things. All right? We've got Ampere's law, and we've got the Biot-Savart law. All right. So Biot-Savart is, let's say, most general. Okay? So you can always apply Biot-Savart and get an answer. Not always easy, okay? It's difficult. But Biot-Savart is most general. No need for symmetry. I mean, of course, symmetry will help there too, but if you don't have it, then you just number crunch. All right, so no need for symmetry. Ampere's law, on the other hand, we need stuff. So Biot-Savart is harder to work with. Okay, but I think we're going to have a case or two where we'll actually do Biot-Savart. But Ampere's law, so there are some rules, right? So Ampere's law will be pretty much our go-to because we don't want to make this class too difficult. So okay, but there are times, right? There are times when Ampere's law is not going to cut it. So what are the rules for knowing? Or actually, rules for knowing to use, or knowing how to use Ampere's law. All right, well, the first thing is you want to look for symmetry. And in our case, we had a circle around a center radius r. Okay, so that was our symmetry. So nice. And that's going to be a very popular symmetry for us. What's the next step? You find the symmetry. Then you use the right-hand rule to find the direction of B. Third, we're going to choose a loop path of integration, okay? And I did my loop path backwards to the B field, whatever. It doesn't matter. I think I drew my B field backwards. poor illustration, I guess. I suppose you guys might be upset at me for doing so. So here's what I'll do. I'll tell you what I'm going to do. I'll do something like this. Brr, brr, brr. And I'll draw my B field the proper direction. Okay? So, good. Now, hopefully everybody is still on board. Okay. So, fine. So you use the right-hand rule, you find your direction, you choose your loop path. And ours happen to be perfectly circular. You need to know, so you're going to have to either calculate or be given the current. Okay, so if you don't know the current, you got to calculate it. Not terribly hard, but you figure it out. Why? Because we need to know mu naught I on one side of the equation, right? I'm gonna write it like this. B times our integral dl. Okay, this will give us something. What it gave us before was 2 pi r, but it'll give us whatever our symmetry happens to be. It'll spit out something. So you need to know what this I is. So you have to calculate I. There's no way around that. Okay, so 5. Then you do your thing, right? Hopefully you have a loop, some kind of a loop. So you need to have a loop. That's a terrible idea. You really want a loop that's kind of like this so that you can get your 2 pi r out of it. But you do the integral. Okay, so this integral has to get done, all right, on your loop. Be like Nike and just do it. So then the last part is cake. You equate whatever that is. You say, okay, I've got one side of the equation. We're going to dot it. And I've got the other side of the equation because I've calculated we know what mu naught is, and we've calculated I. So we've got everything. We equate them and just solve for B. And that's it. So, okay. That is amperes. Now, of course, we started talking about Biot-Savart first, so let's get back to Biot-Savart for a second. Biot-Savart cases. What's a case where we can use Biot-Savart? Well, we'll have, let's say we have some current going through this section of wire. All right, and the wire has a length L, and of course our DL is here, and we'll have some point P out here that we want to know what our B field is at that point. And we'll say, oh, yeah, I can do this because I know the distance x, this distance x, and I know that I can do, oh, not a bad little little drawing there. Here's my theta. I'm gonna call that phi. And let's continue. Okay. So what is R? Right? What is R? Well, we need to know okay. I'm going to change up the situation because, I grabbed the wrong one. I'm going to change up the situation because, first of all, I really want, what I really want, I forgot we need to use the small angle approximation. Okay, so here we go. This is our R, and DL is really small. Okay, so I've drawn it pretty large, but imagine DL is really, really small. So what is R equal to? R is equal to x squared plus, in this case, I'm starting at the very edge, L over 2 squared. All right? We'll get back to this in a second. This works because we're using the small angle approximation. I talked last semester about the small angle approximation with my students, and some of you were not a part of my class, so I don't know how well you know the small angle approximation, but as long as phi is less than 10 degrees, okay, 15 on a good day may be okay, but we're gonna, for our class purposes, phi has to be less than 10 degrees, okay? Let's just go with that. So how do you get phi? Phi is equal to the arctangent of our y over x, right? So y is L over 2, x is down here, and we do that. We do our arctangent of those things, and we should have phi. If phi is not less than 10 degrees, this Biot-Savart thing isn't going to be something you can do. Other people, not even me, no, I could do it, I just don't want to. So yeah, just keep it small, keep your angle small, and everything will work out, okay? So let's say that L is equal to 0.02 meters, okay? That's small. And x is equal to 1 meter. So good. Our angle then, phi, is equal to 1.15 degrees. So this should work, okay? So we're going to say, great. What is theta? Theta is 88.9 degrees. So far, so good. Everybody's happy. And Now, we can do Biot-Savart, and we'll come up with B is equal to mu naught over 4 pi times I times delta L times the sine of phi over r squared. We've already put what r is equal to, and delta L is just basically from one side to the other. So delta L really is equal to L. The sine, well, the sine of 88.9 degrees is essentially 1, right? So good for us. So now I can say that this is really equal to mu naught I times L, delta L equals L, over x squared. And that's pretty good. So, oh, don't forget my 4 pi. Gotta have that. Mu naught over 4 pi, because mu naught is designed to be 4 pi times 10 to the minus 7 Tesla meters per amp. Tesla meters per amp. Why did I write I? I don't want I want Tesla. Tesla meters per amp. Okay, so look, mu naught I divided, or mu naught, I'm sorry, 4 pi times 10 to the 7 divided by 4 pi is just going to be 10 to the 7. So this is why mu naught is defined the way that it is, okay, because that 4 pi cancels out all the time, and you end up with 10 to the minus 7. So all we have to do then is figure out what our current is, the length of our thing, and the distance x that we are away. Okay, so let's introduce some of these things. I don't think I said what the current was. Current is equal to 1.5 amps. And RB, let's do the absolute value of it, is then 10 to the minus 7 times 1.5 times 0.02, and then we're going to divide by 1, because 1 squared is 1, and that is going to give us something in Teslas. What is that number? B is equal to 3.0 times 10 to the minus 9 Teslas. Okay. I have this trash can in here that opens up every time I say open can. But when I say okay, it thinks I'm saying open can, and then it opens. That's the noise. If you keep hearing it, that's the noise you hear. Okay, we can do the same thing for a curved wire. So let's come in here. We've got this we've got a curved wire, and then we've got this. We've got current coming in through the wire. We've got a point P right here. It's a constant radius, our wire. All right. And it's our point P that we want to know what the B field is. The current's going to come in, it's going to go out. And R equals a constant. Let's divide this so that we aren't thinking about the other stuff. And what else do we need to know? There's going to be some angle, theta. Our little section of dl right there. And of course, we know which way the current is flowing through there. I think that does it. All right. So our B is going to be equal to mu naught I. I always say mu naught I because mu naught I goes together all the time, but no, this is Biot Savart. So we're going to do it along the wire. And I've got this IDL cross R. And we're going to divide by R squared. Cool. Now this has really got multiple parts, right? This integral, because we're going to go along the wire. So we're going to start up here at A. We're going to come out down here at B. And we're going along the wire. But this part right here, this cross part in this region right there, is going to leave us with no B field from this section. So this section produces nothing. This section produces nothing. The whole thing, until that current turns and goes around this loop, or around this bend, it's not going to give us anything. So that's the first thing to note. So we're really going to go, our DL is really going to go from here to here. Okay. All right. So far, so good. So in that case, let's figure out what DL cross R is. And it's really DL cross R hat. All right. So that's fine. That's our R d theta. R d theta. Now why? Okay, so we're going along DL. So DL cross R, right? DL cross R. What does that leave you? That leaves you with theta hat. Okay, now you guys are like, but wait, theta hat is still in the same direction as DL. I don't get it. What are you talking about? So here's our unit vectors. Here's R, okay, and you think that this unit vector is your theta hat, but it's not, okay? Theta hat is really, if you're going in this circle and you use the right-hand rule, you put your fingers along that circle and you point your thumb into the page. That is theta hat. All right? So theta hat is really not this direction, okay? It's into the page. So we've got DL cross R. So here's our DL. Cross R is giving us theta hat, all right? And they're all 90 degrees to each other. So it's hard to remember that theta hat does not, it's like torque. It's the same as torque. Torque is in theta hat. Theta hat is always perpendicular to the rotation. It's orthogonal. It'll either be up or down depending on whether you go clockwise or counterclockwise. Okay, so now we've got R, which is a constant, so we can factor R out, and we're left with B. I'm going to drop the vector sign. We're doing absolute magnitudes here. So 4 pi r squared, because r's are going to pop out. I've also got an r on top that's going to flop out. And I'm going to be doing my integral from 0 to theta, but theta is pi over 2. All right, and d theta. I think that covers it. So cake, B, this is going to cancel that. Pi, so I've got mu naught over pi cancels, 2 times 4 is 8. And I've got my current flowing. I dropped my current here. And let's see what else. Pi is gone. Oh, and I'm left with R on the bottom. So I don't like that B. That's a terrible B. And there you have it. So for this quarter circle, B is equal to mu naught I over 8R. If we were to go around the whole loop, right, we'd multiply this thing by 4, and we'd have, this is whole loop. We'd have 4 times this, which would be mu naught I over 2R. This is what we got, or what we will get when we do our thing. Now, what is our direction? All right, what is our direction? Well, the direction is the same as theta hat, right? We did the cross product. We're in theta hat, so let's just stick theta hat on this whole thing. All right, and we figured it out already, but that theta hat is into the page. Okay, so that's what we've got. Okay, I'm going to do this last one. I'm going to do this last one and save the rest for Tuesday. Or maybe I'll record another video in the morning. I don't know. This stuff is sometimes gets a little dense for people, but let's do this last one, okay? So a long straight wire. Here's our long straight wire. It's as straight as I can draw. Imagine a straight wire. We've got positive and negative infinity on this thing. And we're coming down here to point P. And we want to know at this point P what our B field is as we go through these little sections of dx. And of course, here's our radius r. And you know what? I don't even like having, let's say that we are, let's say we're some length L away. I'd rather do L. I think the book uses R, and I don't know. That's confusing. Big R. No, gosh darn it. I guess the minimum, we could call it big R, which is equal to R. Big R is equal to R min. Sure. Okay, why not? Okay. So we have to do some stuff. First of all, if we say that this point right here is x equals 0, then we can work with whatever the value of x is, and we can cut this whole problem in half, and we can go from 0 to infinity and then multiply by 2. Okay, so we could do just this side and multiply by 2, whatever we get. That's fine. You can do that, or we can integrate from negative infinity to infinity. That works too. However, okay, so first let's write down B of R. B equals mu naught over 4 pi. And we've got our wire, and we've got our I dl cross r hat over r squared. Okay. See, there goes the can again. I always say okay, and the can goes up, and everybody's happy. What is r first? Let's lay that down. R squared plus x squared square root. All right? And let's see, I didn't label this theta. R happens to equal r sine theta. Okay, that's true. So the sine theta is equal to big R over little r. All right? Well, what is this going to produce for us? The sine of theta. So now we can write B equals mu naught over 4 pi. And I can factor out my current I because it's a constant. And now I've got an integral of dl sine theta, which I'm not going to write. Well, okay, I will. Sine theta over r squared. But I'm going to rewrite all of it. Our integral r over r cubed dl. Okay. Yes. Love it. Okay. There goes the can. So r cubed. Well, r is equal to the square root r squared plus x squared. So if I say it's to the 1/2, if I say this is cubed, then this is to the 3/2, okay? So that means that b is equal to mu naught I. R isn't going to change, so I've got R there. I've got 4 pi, and I'm going to do the integral of dl from negative infinity to infinity because I don't want to multiply by 2, and this isn't going to be too difficult, but I still have to divide out by r squared plus x squared to the 3/2. All right, but dl is really dx, right? dl is equal to dx because that's the direction that we're going to go. So I'm going to erase dl. In fact, I'm going to erase all that. I don't like how it looks anyway. And we're going to say dx over r squared plus x squared to the 3/2. And this is where we have to do our lookup on the integral tables, or I don't know, whatever you want to do. You go out there and you say, what is this integral? So you say, what is the integral of du u squared plus a squared to the 3/2? And that ends up giving you 1 over a squared u over u squared plus a squared to the 1/2 plus c. Well, that c is going to go away because we're going to evaluate this between negative infinity and infinity. So let's write down our b. b equals mu naught I over 4 pi. Now I had r on top, and now I've got r on top, but this is equal to r, right? Because my a is r. So a equals r. So I've got r on top, r squared on the bottom. That leaves me with an r on the bottom. And I now have x on top, that's the u. And I'm left with x squared plus r squared to the 1/2. And I'm going to evaluate that all at negative infinity to infinity. How do you like my Laverne and Shirley infinity sign there? Okay. Negative infinity. So that negative infinity is going to go in here, and positive infinity is going to go in there. And we're essentially left with infinity over infinity. One's positive, one's negative. That equals positive or negative 1. Well, the top one's positive, the bottom one's negative. And that leaves us with you guys might not like what I'm about to do, but I want to do it just so that we keep everything on the same page here. That leaves us with 1 minus 1. So, nice. What is 1 minus 1? That's 2. So the whole thing ends up being 2 times mu naught I over 4 pi r. The 2's and the 4's get together, and they, man, what is going on with my... They conspire together to give us 1/2. those 2s and 4s. It's a conspiracy. And again, we've got mu naught I over 2 pi r. Oh, well, I shouldn't say again. You haven't seen that yet. Okay. So that works pretty well. So Biot-Savart is definitely doable. And I think what we should do is stop there. And I'll post these and produce. I think I'll do another video in the morning. Okay, thank you very much for your time.